Professor Ji-Yuan Li of Shanghai Center of Mathematical Sciences. The title is Twisted Derived Equivalence for abelian surfaces. So please.
Thanks for the invitation. So today I'm going to talk about the twisted equivalence between abelian surfaces. Actually, this work is largely motivated from the work on K3 surfaces. Yeah, and hopefully I will explain to you that the story on K3 and then explain what's happening for abelian surfaces. So let's start. So the motivation is from so-called Torelli theorem on K3 and abelian surfaces. So let's just briefly recall what's the Torelli theorem for K3 surfaces. So recall that a smooth projected surface over K is K3 if there's no homology for structure shift, and also it has nowhere degenerate algebra 2 form. Or in other words, the canonical bundle is trivial. So if K equals to C, then we can also talk about non-projective surfaces, still just some Kähler surfaces, and satisfy these conditions. So if K is a complex number, and we can definitely study more general surfaces, yeah. And in this case, the cohomology theory has a natural structure called the Hodge structure. So basically the singular cohomology, the H2XZ has a width 2 Hodge structure. So it's decomposed into 3 pieces. And the H20 is generated by this holomorphic 2 form in this case. And the H02 is the anti-holomorphic 2 form, where H11 actually is, sorry, it's not Picard, sorry. This is wrong, this is not Picard. Just H11 is just a 114, so this is a typo. And what's this structure tells us for K3 is very interesting. So we have the well-known, the global Torelli theorem for K3 surfaces. So basically this tells us if we have two complex K3 surfaces, and if their second cohomology is isomorphic as the Hodge structures isomorphic, and also as it's also this isomorphism preserves the coproduct, basically preserved the intersection form, then this is equivalent to say that these two K3 surfaces is isomorphic. They are isomorphic. Okay. So here at HS means this is a isomorphism and the preserved Hodge structure, and also is an isometry. Okay. So I didn't say isometry, but here it is actually an isometry. If it's not isometry, then people don't know what this is. Yeah. So this is the global Torelli theorem, and one can make it more precise. So if this Hodge isometry, we call integral Hodge isometry, and it sends a Kähler class to a Kähler class, then it will be induced by some isomorphism between X and Y. So in other words, actually this global Torelli theorem just saying that the Hodge isometries between K3 surfaces are algebraic. Yeah. So one is wondering, okay, it seems that the condition 2 that such Hodge isometries is induced by isomorphism is algebraic, but you can take some autoequivalence that so every integral Hodge isometry up to some autoequivalence will be some Hodge isometry satisfied to condition 2. Yeah. So it will send some Kähler class to Kähler class. So I didn't mention the proof because this is not that important, but just to remember that this global Torelli theorem basically tells us the Hodge isometries are algebraic. Okay. So the question just arises just for rational Hodge isometries, basically because we have the integral Hodge isometries are algebraic. This is predicted by the Hodge conjecture. And the Hodge conjecture also predicts the rational Hodge isometries will be algebraic. So this is a natural question that about the algebraicity of rational Hodge isometries. And this has been done in the last few years. That the first one is proved by Buskin, that he shows that the rational Hodge isometry is algebraic because it can be it occurs as some Chern class of some hyperholomorphic shapes. Yeah.
Excuse me. So are you assuming that the surface is algebraic?
Yeah. Here I have to assume that it's algebraic. Yes, but even it's not algebraic, it's also still some hyperholomorphic shift. It's also some Chern class of hyperholomorphic shifts. Yeah, because hyperholomorphic shift also lives on. But it's not algebraic, but it's just some holomorphic. Yeah, yeah, just some Chern classes of some hyperholomorphic shifts. Okay.
Thank you.
And the second one is definitely we need the algebraic. Yeah, everything is algebraic. Here I cannot say algebraic, but it's some related to some hyperholomorphic shift. Yeah. Okay. And for the second one is there's another proof by Huybrecht. So if you go to the lecture last night, then he talked about this one. And actually, there is a motivic description of rational Hodge isometries. Basically, this can be viewed as some twisted derived equivalence and defined as follows. So this is defined by Huybrecht. So we say X and Y, the two case-rich surfaces, are twisted derived equivalent if there is a Feynman twisted case-rich surfaces, the Xi, alpha I, and Xi beta I. So here, twisted case-rich surfaces just means case-rich together with the Floer class. Yeah. Later, I will give more details. So here, just pretend that everyone knows twisted case-rich surfaces. Yeah. And so given such a twisted case-rich surfaces, and it will give a chain to connect X and Y as follows. So basically, X alpha is derived equivalent to X1 beta 1, and there exists some alpha 2 that the X1 alpha 2 is the derived equivalent to X2 beta 2, and keep going, and until you end to Y. Yeah. So this is the definition. Okay. So given this one, and basically Huybrecht and also later Fu and Via, they show this twisted derived Torelli. Or they also call this motivic Torelli theorem. So they show that if we have two complex case-rich surfaces, and the following statements are equivalent. So first we have the rational Hodge isometry. And the second one is just that we have the rational Hodge isometry between the transcendental part of two case-rich surfaces. And the third one is we have a rational Hodge isometry. So, sorry, here it should be that there is Hodge isometry. And between the Mukai lattice, yeah. And the fourth one is that we have this isomorphism of the Chou motifs. And it is also as some Frobenius algebra. Basically, Frobenius algebra just this is isomorphism and also is multiplicative. Okay, yeah, just multiplicative. And the last one is this: the previous four conditions are all equivalent to the last one, just the derived equivalent, twisted derived equivalent, defined by Huybrecht. Yeah. Okay.
Sorry, for the fourth statement, is the Chou motif defined over Q?
Yes, over Q.
Thank you.
Yes. And basically, one can view that 1, 2, 3 are some we call cohomological realization of twisted derived equivalence. Yeah. So the rational Hodge isometry is just some natural Hodge theoretical realization of the twisted derived equivalence for when k equals to c. Yeah. So for complex number, we have Hodge theory. And the name is largely motivated from this well-known derived probability theorem, basically proved by, sorry, the typo, the Mukai and Orlov. So basically, two K3 surfaces are derived equivalent if and only if their transcendental part, the integral transcendental part, are Hodge isometric, and also their Mukai lattice also are Hodge isometric. Yeah. So these three conditions. So integral Hodge isometry corresponds to some derived equivalent, and the rational corresponds to some twisted derived equivalent. So the philosophy is as this. Okay. So let's give a quick overview of the proof. So for derivatorily, the idea is as follows. So given some derived equivalence phi, and they induce a map on the Mukai lattices. So we take the image of 0, 0, 1, okay, and then we can use the theory of moduli space of sheaves. So basically, we have we consider the following moduli space. So the actually is just some V generic ample line bundle. So we consider the Jessica H stable sheaves on X with the Mukai vector V. Okay. So in this case, and basically Mukai shows that this will be a K3 surface because V is the image of phi, and phi, the induced map phi on the Mukai lattice will preserve. It will preserve intersection form, which is will be a isometry. So V squared will be 0, and so you will get that this one is still a K3 surface. So the dimension is 2, so it's a K3. Okay. And then you can consider the composition, and from dBx to the dB of this the new K3 surface constructed from the moduli space of stable sheaves. And the composition will send 0, 0, 1 to 0, 0, 1. Okay, so the first one is the given one is phi. From dBx to dBy is phi, and the second one, the derived equivalence is given by the Fourier Mukai transform induced by this universal sheaf P. So consider this moduli space of sheaves. So we have a natural universal sheaf lying over Y cross product with this MHYV. Yeah. So these are naturally derived equivalent. Okay. So then we have this. We can use the Hodge realization. Basically, if we have the because we have this Hodge isometry between the Mukai lattice of X and this the moduli space of sheaves, and also stands 0, 0, 1 to 0, 1, and just a little bit fundamental calculation just shows that this will force there will be a Hodge isometry between the integral cohomology of X and the integral cohomology of, sorry, not, this is MHY. I should make the pen here. Not Y, this is a typo. This is the MHY, okay. And then shows that X is isomorphic to this moduli space of sheaves on Y. So this is not Y. Okay, so this is just a simple proof of this derived Torelli theorem. So the idea is just use some autoequivalence and change the Mukai vector, and so that it sends 0, 0, 1 to 0, 1, and the rest of it just follows from the global Torelli theorem. Okay. And similarly, that we can go to the Daniel's proof, the Huybrecht's proof of the twisted derived Torelli theorem. So he first characterized the derived equivalence between the twisted abelian surfaces, K3 surfaces. So So basically, we can follow the proof of Dirac-Torelli theorem and show that the reflexive Hodge isometry. So there is a special Hodge isometry. It's not an arbitrary rational Hodge isometry, but we call it reflexive. It's very close to integral Hodge isometry. Okay, so such isometry is equivalent to the derived equivalence between the twisted K3 surfaces. Okay. So this I will define later. Okay, so in later we'll see the details of this proof. But the idea is similar. Just you construct instead of construct modular space of sheaves, you construct a modular space of twisted sheaves, and show that Y is isomorphic to the modular space of twisted sheaves on X. So that's the idea. So everything is very similar to the previous one. Just replace X and Y by X and alpha and Y beta. So X replace X by X alpha, Y by Y beta, and you just follow this proof, and that's what we can say. Yeah. So the first step is just parallel to the Dirac-Torelli theorem, and the other part is just the classical Cardan-Dieudonné decomposition that saying that any rational Hodge isometry can be decomposed into the decomposition of Feynman reflexive Hodge isometries. Yeah. So then this is basically gives what we want. So we just simply decompose rational arbitrary Hodge isometry into Feynman such a special Hodge isometry called reflexive, and each step is a derived equivalence between these twisted K3 surfaces. And yeah, okay, sorry. And following this, there are proofs, and one may ask simple some similar questions. Just what about positive characteristic? Yeah. So can we characterize the twisted derived equivalence? Because here, if you look at our definition, so I go back a few steps. So if you go to the Daniel's Huybrecht's definition, so here it doesn't require anything about the fields, right? So because this one, the twisted derived equivalence actually can be defined over any fields. So just connect two K3 surfaces are connected by a chain of twisted K3 surfaces. Okay. So this definition is valid for all the fields. So our simple question just whether we can have some cohomological realization of such twisted derived equivalence. The problem is that we don't have a Hodge theory, and actually the global Torelli theorem is still missing for positive characteristic fields. And another question is what about abelian varieties? Because on abelian varieties also there is a very beautiful derived equivalence relations, and over complex numbers, we also have many nice cohomological realizations for such derived equivalence. Yeah. Okay, so let me just mention some conjectures with respect to the first question. What about in positive characteristic? So the idea is that in positive characteristic, one have to use all the cohomology theory, all the includes the L-adic and also the P-adic cohomology theory. So there's a candidate. This definition is defined by Ziquan Yang 2 years ago. So he say that the two K3 surfaces are isogynous if there exists some algebraic correspondence between X and Y, and this algebraic correspondence induce some isometries. Okay, so between X and Y. Here the isometry on L-adic part just between their Ital cohomology, and the P-adic just between their crystalline cohomology. And we may say that this is prime to P isogeny if Fp is integral, which means this isometry is actually defined over the integral crystalline cohomology. Okay, so basically the integral crystalline cohomology are isometric. Because this isometry is induced by algebraic correspondence, so it's algebraic, so automatically algebraic. So definitely this naturally this isometry is also Galois equivariant. So okay, so they are also isometric as Galois modules. And here for crystalline cohomology part, they are isometric as F crystals. Okay. Okay. And here is the conjecture. So actually, one motivation of this work is motivated by this conjecture. So we first want to verify this, to start this question, and then we found we first work out over the abelian surfaces, and then try to apply some techniques to show this conjecture. So I will mention how to attack this conjecture, yeah, at the end of this talk. So the conjectures here is just about two K3 surfaces over some perfect field. Okay, so this field will be in positive characteristic, and we believe that the following conditions are equivalent: that x and y are prime to P twisted derivative equivalent, and there exists some prime to P isogeny, prime to P isogeny in the sense of Young between x and y. Okay, and the last one is their integral crystalline cohomology isometric as a K3 crystal. Yeah. So the last one is some cohomological realization of the twisted derivative equivalence. So over positive characteristic fields, the interesting thing is you have to be careful, because there is when the order, yeah, when the order is P, okay, there will be some trouble, and we doubt whether we can remove the prime to P. Yeah, this is the only thing we need to be careful. Yeah. For example, if we have a K3 surface, and and also it's a Forbidis Purbach, and there is also some isogeny between this cohomology theory, and we think that in general they are not, yeah, they are not twisted derivative equivalent. So that's the only case we worry. Yeah. So that's why we want to add the condition that prime to P. Yeah, this is very natural in positive characteristic. But I also can say something if it's actually not prime to P, but it's not inseparable. If it's separable, still something we can say something. Okay. So this is the motivation. Okay. Any question? Okay.
So I'd like to say, what's the relationship between this 1 prime, 2 prime, and 3 prime?
So okay. So first, 3 prime is the weakest, right? So 1 and 2 also can always imply 3, right? So 2 implies 3 just by definition, right?
Okay.
So the difficulty is the converse, right? The converse is 3 implies 2 and 3 implies 1.
Okay, thank you.
Yeah. And the 3 implies 2, this is actually the Tate conjecture. So this is algebraic and the standard conjecture. Yeah. So this is algebraic. So because in our definition, we need that this is induced by some algebraic correspondence. So we need algebraicity. Okay. So the converse to this direction is Tate conjecture, and then to this is derived Rayleigh. Yeah.
Okay. Okay. Thank you.
This is derived Rayleigh. Yeah. Okay. Any other question? Okay. Let's go to the second part. So I will briefly talk about the derived equivalence for between abelian surfaces. So this is also kind of well-known, the derived Rayleigh theorem for abelian varieties, and this is over all the fields. Okay. So for x and y are abelian varieties, and the following are equivalent. So if x and y are derived equivalent, then it's equivalent to say there is some symplectic isomorphism between x cross with the x dual to y cross with the y dual. Okay. So in particular, because of this existence of such symplectic isomorphisms, so if x and y are derived equivalent, then we have x and y has to be isogenous. I mean, here isogenous is just the standard isogenous between abelian varieties. Okay. So there is a finite map between them, surjective and finite map between them. Okay. And symplectic just means the following. Yeah. You take the inverse is given by the dual. Yeah. Symplectic. This is just symplectic. So this is a very beautiful classification of the Fourier partners of abelian varieties. And it also has some nice realizations, like when k is a complex number, the condition 2 basically is equivalent to this Hodge isometry, just H1 of x cross product with x dual to y cross product with y dual. Yeah. There's a Hodge isometry. It's also isometry. Yeah. But in general, x being isogenous to y doesn't necessarily imply that these two are derived equivalents. Yeah. So one may wondering, what about add twisted derived equivalence? Will x being isogenous to y is equivalent to the twisted derived equivalence? Yeah. And actually, for abelian surfaces, we will give a completely answer to this question, such question, just the relation between the derived or twisted derived equivalence and the isogenous between abelian varieties. Okay. Let's just say a few words about the derived equivalence for abelian surfaces. So here, so suppose X is a abelian surface over K, and we take Hx to be the Mukai lattice, and sometimes we do denote the algebraic Mukai lattice if K is not C. If K is a complex number, Hx will denote the Mukai lattice, which is over Z. If K is not complex number, I also want a Z structure, so I will use Hx to denote the algebraic Mukai lattice. Okay, given such a lattice, and we can consider the modular space of stable shifts on X. Okay, so this construction is parallel to the K-series. So you just define this, the stable shifts on X with Mukai vector B. Yeah. So one can characterize the Fourier partners of abelian surfaces by these modular spaces. So roughly speaking, this is also realized by Orlov and recently by Honig's, Lombardi, and Terabasi. So if two abelian surfaces are derived equivalent over arbitrary field, and this will be equivalent to say that Y or its dual is isomorphic to some modular space of sheaves. Yeah. For some V. So here V satisfying the condition V squared is 0. Okay. So this is also a simple characterization using this modular space of stable sheaves. Yeah. And we also have some second cohomological realization. This is found by Shioda. Also, basically, when K is C, that is complex numbers, and two abelian surfaces are derived equivalent if and only if their transcendental lattice are Harsh isometric, and also this equivalent to their Mukai lattice are Harsh isometric. Yeah. So if you find this story is very similar to the story of K3 surfaces, right? If you look at this theorem, and the only difference between the K3 and the abelian is for abelian, you have to notice that the dual of the abelian surface is also its Fourier partner. So you have always have some dual here. So Y and the Y dual is isomorphic to some modular space of sheaves. Yeah. So for K3, there's no dual construction. So just the K3 surface will be isomorphic to some modular space of sheaves. But the cohomological realization is important. Just that's what. Just we want to show that such one, because this someone go to relate to some interesting conjectures like the Hodge conjecture and also the Tate conjecture. So we are kind of interested in such questions that we want to have a cohomological realization of all the derived equivalence or twisted derived equivalences. Okay. So let's define the twisted derived equivalence for abelian surfaces. So here is a definition for twisted abelian surface. So X is an abelian surface, and we consider it's a cohomological Brauer group. So basically, it's the second Itau cohomology of GM. And a twisted abelian surface is just a pair that X and alpha. Alpha is some Brauer class. And it's also equivalent to given GM gerb, just X mass curve X to X. Yeah. Sometimes people will also use mu n gerbs. Then this is not the cohomology of GM. It's the cohomology, second cohomology of mu n. Yeah. If you want to replace the GM by mu n, then you get mu n gerbs. Yeah. Okay. So that's the standard definition for twisted varieties. Basically, you just choose some broad classes, yeah, or some mu-n, some classes in mu-n cohomology. And then we can define the twisted derived equivalences. So two abelian surfaces are twisted derived equivalent if it's connected by equivalent. Sorry, this shouldn't be the twisted, by equivalence between the twisted abelian surfaces. So X alpha starting with X some alpha and then ends to Y with some beta. Yeah. And here I can explain what's called the prime to P twisted derived equivalence. So look at this diagram that starting with some X alpha and go to some X1 beta 1. And then there's some alpha 2 and go to X2 beta 2 and so on. And I can say that it's called prime to P if the order of this broad class of alpha I is prime to P. Okay. So P is not divisible, cannot divide this order. Okay. So I call this prime to P. So basically this there is some numerical invariant here, yeah, just occurs as the order of the broad class. Okay, so you may ask, oh, there may be not a unique decomposition like this. Yeah, this decomposition is not unique, but if there exists such a decomposition satisfying this prime to P condition, I will call such a twisted derived equivalence prime to P. Okay, so yeah, the equivalence is not unique. the decomposition is not unique. Okay. And we can give a characterization of twisted derived equivalence. So here is just a copy the theory of untwisted derived equivalence. So roughly speaking, I replace I replace x by x alpha, a twisted abelian surface, and h x by h tilde x alpha. This is a so-called twisted Mukai lattice. And this definition is a little complicated because it really depends on the fields and the B field theory. So I decided to omit it. This can also be defined. Yeah. So you define this twisted Mukai lattice, and we can define some modular spaces. Modular space MH X alpha V is the modular space, is the cost modular space of twisted shapes on X with given Mukai vector. Okay. And everything is very similar to the case 3 so far. Just when V square is 0, it's an abelian surface, whereas if it's non-empty. Yeah. And for dual, it's also, we can define such a theory. Yeah. And there's a theorem, and first it's proved by Yoshioka, and later, in some cases, proved by me and my student Haitao Zhou. So when the characteristic is positive, and I assume that either P cannot divide the order of alpha, or X is super singular, and we will have a derived equivalence between two twisted abelian surfaces if and only if Y or its dual is isomorphic to the cost modular space, okay, for some V. The proof is very standard, and basically everything you can follow the proof of in category 0, or also follow the proof of K3 surfaces, except you need to prove that the modular space, the cost modular space, is non-empty. Okay, so that's why we make such a weird conditions here that when the order is coprime to P, yeah. When the order is coprime to P, basically this is the result follows from, this is proved by Yoshioka. But the problem is we have to deal with the case when the order is not coprime to P. For example, if X is a super singular abelian surface, then we can show that its broad class is a P torsion. So that means every broad class is of order P. So in that case, yeah, we have a different approach to show that this is still valid. Yeah. So yeah, in possible characteristic, you have to be careful when the order, yeah, is not coprime to P. All right. So with this one, there we'll have a cohomological, we'll have a modular space to classify the twisted derived equivalence. Okay. So then it's ready to introduce to the twisted derived Torelli theorem for abelian surfaces. Okay. So before I state the main theorems, I first introduce a notion that the quasi-isogenous of degree 1. Okay. So for two abelian surfaces, X and Y, we see that X, Y are quasi-isogenous of degree 1 if there is a quasi-isogeny, okay, F, is from X to Y, this is map, and the rational coefficients, and the degree is 1. Okay. Yeah. So if the degree is 1, degree can be viewed as the fiber between X and Y, and we will see that it's prime to P if the coefficients, yeah, is lying in Q intersect with ZP. So basically, you can think of this as a matrix, and the coefficient is rational coefficients, and the denominator is coprime to P. Okay. This is what we call the quasi-isogenies of degree 1. So why this notion is important? Because this is our main theorem. So we first give a twisted derivative theorem in category 0. So if we have two smooth abelian surfaces over K bar and the characteristic is 0, then the following are equivalent. So X and Y are isogeny, and degree 1 isogeny, quasi-isogeny. Okay. Basically, the X and Y are degree 1 quasi-isogeny. And the other one is X and Y are twisted derivative equivalent. And third one is still we can use motives. So the Chor motives between X and Y are isomorphic as an exterior algebra. Yeah, because we know the motives of abelian varieties are exterior algebra. So we have such a isomorphism. And the even, all equivalently, you can only look at the even part. The even Chor motives are isomorphic as Frobenius algebra. So this 2 and 4, you can think this is the parallel to the story for K3. And the 1 and 3 actually are something classically from abelian varieties. Because for abelian varieties, people usually use the first cohomology groups. And for K3, people use the second cohomology groups. They use the even cohomology groups. So 1 and 3 using the first cohomology groups, and 2 and 4 using the second cohomology groups. So this is in for over category 0. Okay. Any question? Okay. So when K equals C, then we have the following cohomological realizations. Yeah. So everything just can be realized as the Cauchy isometry between some cohomology uneven cohomology part. Like for example, their second cohomology are rationally Cauchy isometric, or their Mukai lattice are rationally Cauchy isometric. Or you can also use the transcendental part. Yeah. So roughly speaking, this tells you the rational Cauchy isometry between abelian surfaces are algebraic. In particular, this implies this. Yeah. But because for abelian fourfold, the product of abelian surfaces, the Cauchy conjecture is already known. So people a priori already know that such a Cauchy isometry will be algebraic. Yeah. Here we can tell you this also comes from either twisted Fourier-Mukai transform or induced by some quasi-isogeny. Yeah. So the algebraicity can come from two sides. One is quasi-isogeny. The other is the twisted derivative equivalence. Okay. So that's the interesting part for abelian varieties. So yeah, we have the isogenies, which can also induce a lot of rational Cauchy isometries here. The really interesting part for us is for positive characteristic side. Yeah. So we also proved the twisted derivative theorem in positive characteristic. Yeah, this is kind of interesting for our purpose. Yeah. So category 0 part basically follows a standard proof of Daniel and Orlov and Mukai. But for category 0, this is much more interesting because a lot of things is missing. So let me just state the theorem. This is still a result joined with my student Haitao Zhou. And So suppose given two abelian surfaces x and y over an algebraic closed field, and I will assume that the characteristic of this field is odd, so p is greater than 2, and then the following two statements are equivalent. So x and y are sorry, this prime to p derived by isogeny. I should say that derived by isogeny is also just means twisted derived equivalence. Yeah. In our paper, sometimes we also call this derived by isogeny, follow Yang, but this is just a twisted derived equivalence. Okay, and this is equivalent to x and y are actually prime to p quasi isogenies of degree 1. Okay. Okay, so there is a natural connection between the derived equivalence, twisted derived equivalence, and the quasi isogenies on abelian surfaces. So one can see from here, in the isogeny class of X, not everyone is derived equivalent twisted from Mackay partner. So only there exists degree 1 quasi isogenies. There will be some twisted Fourier-Mackay partners. Yeah. Here also I add the natural condition prime to p. Yeah, because this is in characteristic of p. But there is an interesting case. So if X is supersingular, okay, then Y is twisted derived equivalent to X if and only if Y is supersingular. That means that any two supersingular abelian surfaces are twisted derived equivalent. Okay. So this is yeah, this is also natural because for case 3, this is also known. For supersingular case, it's actually easier than the non-supersingular case. And in the case when K is finite, we also have some simple cohomological realization by using the crystalline cohomology. So when K is finite and the conditions above is equivalent to the not Hodge equivalent to some isometry as K3 crystals. Yeah. So we also have a nice cohomological realization. Okay, 10 minutes. Any question? So from here, in particular, this also shows that this isometry are algebraic. Yeah. So this proves the Tate conjecture between the isometries between the crystalline cohomologies. So let me just quickly recall the twisted derived Rayleigh theorem over C. That there is an equivalence between the rational Hodge isometry and the twisted derived equivalence. So this is also this proof is basically the same as the case series. So there are not basically there are no difference. Yeah. Just to replace K3 by abelian surfaces and some fixed marking, and we define so-called reflexive Hodge isometry. Okay, so reflexive is in this. So in this sense, so it's induced by some reflection. So reflexive just means this is basically a reflection. So for such reflection, okay, and we can characterize such reflections by the twisted derived equivalence. Yeah. So basically, this is when there is a reflexive Hodge isometry, and it will induce by some derived equivalence between twisted abelian surfaces. Yeah. So this is standard. So this is the proof is not that interesting. Yeah, and then similar there will be some Cardan-Dieudonné decomposition that any rational Hodge isometry will decompose into some Feynman-Manning reflexive Hodge isometries. Yeah. So this is what's happening for K3 and also for billion surfaces over C. So for over C, not that interesting. Okay. The B3 part is for positive characteristic of fields not defined over C. Okay. So let me just say some words about the relation between the isometries and the twisted derived equivalence. So if we have two abelian surfaces, x and y, if they are prime to p twisted derived equivalent, and the twisted derived equivalent will induce isometry between the F crystals. This is the standard. But at the same time, if you look at the prime to p quasi-isogeny of degree 1, okay, the wedge product also introduced isometry between their crystalline cohomologies. So basically, this observation is our the main ingredient of the proof. So we found that the twisted derived equivalence and the quasi-isogeny of degree 1, they both introduce some isometry between the F crystals or the K3 crystals. Okay. So then the problem is whether the converse is true. So whether the isometry will imply the twisted derived equivalence, or the isometry implies the quasi-isogenies of degree 1. So that's why we believe this is true, is people can easily observe this too. Yeah. Okay. So here is the main idea, is we follow Shioda's trick. So recall that so this is a very beautiful trick that very successful over C. So recall that there is a admissible, Shioda introduced the so-called admissible map, just some isomorphism between H2 second cohomology of the abelian surfaces. So admissible if it preserves the Z basis induced by the integral basis of H1. Okay. Because the basis of H2 can be used as some wedge product of the basis of H1. Okay. So we call it admissible. It will preserve such a basis. And Shioda has used this trick to show the following for Hodge isometry. So if there is a two complex abelian surfaces, and we have some admissible Hodge isometry, which means such an admissible map is isometry, and also it preserves the Hodge structure. Okay. The phi is the Hodge isometry, and then admissible. Then there will be isomorphism of Hodge structures between the first cohomology of X and Y, okay, such that the wedge product of phi equals to phi or minus phi. So this tells us, basically shows that such isometry on H2 is induced by some isogeny between X and Y of degree 1. Okay. So this is a Shioda trick over C, but this is integral also. Okay. So what we do is we generalize Shioda trick for L-adic and the crystalline cohomology. So basically, when L is larger than 2, and our result not for just for positive characteristic, it's also for any fields. Even the K is equal to 0. This is also true. So for L greater than 2 and every admissible Galois equivalent isometry, and there will exist some isomorphism of Galois modules on H1. Okay, so basically this is saying that admissible Galois equivalent isometry is induced by some Galois isomorphisms on H1. Okay. such that the wedge 2 of this of the on H1 gives the isometry on H2. Okay, just maybe up to a sign. Yeah. And similar results also holds for the admissible isometry of F crystals. Yeah. And basically, this also gives the Tate conjecture for phi L and phi P when K is finally generated and O K is finite. Yeah, although Hodge conjecture for product of billion surfaces is known, but the Tate conjecture seems to me, I didn't find a reference that Tate conjecture is known for product of billion surfaces over fields, over positive characteristic fields. So please let me know if this is already known. Yeah. So here just some application of this Showdown trick. Okay. And now I can sketch the proof. So I have 3 minutes. It's kind of enough. So from twisted derived equivalence to quasi-isogeny, I can show the following. So first we use some descent trick to reduce the case K is finally generated. Okay, and the characteristic is P is greater or equal than 0. So if it's characteristic 0, then we have the derived equivalence between X alpha and sorry, this is not Y alpha, it's Y beta. This is Y beta, sorry. So we have derived equivalence between two twisted abelian surfaces, and this will implies a Galois isometry for some L, yeah. And then we can apply the L-adic Showdown trick and the Fortin theorem to show there exists a quasi-isogenes of degree 1. Okay. So this is what's happening in characteristic 0. But what happens in positive characteristic is we have to use the crystalline cohomology. Okay. And because we have this isomorphism between the crystalline cohomologies, we have to use the crystalline Showdown trick, and then plus the flat descent of p-divisible groups to show that the two abelian surfaces have isomorphic p-divisible groups. And then by de Jong's theorem that X and Y will be prime to P quasi-isogenes. Yeah. So in positive characteristic, we will apply the crystalline Showdown trick. Okay. This is one direction from twisted derived equivalence to quasi-isogenes. For the converse, so given some quasi-isogeny to twisted derived equivalence, this is more difficult. But fortunately, we have some lifting theory. So given some quasi-isogenes between billion surfaces, we can apply the Tate theory that we can lifting the quasi-isogeny to characteristic 0. And then we can basically, after you lifting characteristic 0 and embed into C, then we can apply the twisted derived directly over C. Okay. And this is so the idea is just that we first lift to characteristic 0 and then do the reduction back to the P. So then when you do reduction, we need the step 3, the specialization of the twisted derived equivalence. More precisely, we prove the following theorem. So if R is a DVR and with relative field K, and the K is a positive characteristic, and but it's odd characteristic. And given two integral models X and Y over spectral R, either families, either integral models of billion surfaces or K3 surfaces. Okay, if the generic fiber are prime to P twisted derived equivalent, and we can show that the special fiber is also twisted derived equivalent. Yeah. So the twisted derived equivalent will be preserved under specialization. So that's first we lift and then we do the specialization. Okay. So there is also a categorization of P divisible the twisted derivatives. That means if given some projective families, sorry, if there is a not prime to P, but it's actually P order twisted derivative equivalence, and we also can show that it corresponds to some special quasi-isogeny. Yeah, the quasi-isogeny is not prime to P, but it will be liftable. Yeah, we just replace prime to P by liftable. Yeah, then that should be also the same. Okay, I think it's time. Okay, sorry, 2 minutes. I think it's time for me to stop.
Oh, thank you very much. Okay. So are there questions?
So I have one question for the conjecture on K3 surfaces. So if you assume the field is finite, can you show the 3' imply derived twisted derived equivalent?
The problem is for K3, currently the problem is, so there are two ways. Either you prove some nice global totality theorem, or you lift into category 0, right? And the problem is we don't know how to lift into category 0 at the moment. Just directly lifting to category 0. For abelian surfaces, we have nice lifting theory because we first reduce the isometry to isogeny. For isogenies, there is a certain theory which can lift it to category 0. But for K3, it's hard to lift isometry between H2. So that's the problem. So our current idea is, we're still doing this for K3s, is we also use Kugasaki to reduce to some H1. Yeah. So H1 is always liftable, but H2, yeah, we don't have nice lifting theory. Yeah. Yeah. You want to lift the cycles, not just the cohomology groups. Yeah. You want a motivic lift because here the quasi-isogeny actually is motivic, so you actually want a motivic lift. So we can lift for example, we can lift the isometry between K3 surfaces to some isometry between Durham cohomologies, but Durham cohomology doesn't give you integral Hodge isometry or rational Hodge isometry over K0. Okay. Yeah, so that's the problem.
Are there other questions?
So can a smooth projective variety have infinitely many twisted Fourier multi-partner?
No, I think there are only finite many. Oh, you mean any projective variety?
Yes.
Oh, I don't know this. I don't know the answer actually. Then I don't know the answer. I think for abelian varieties and yeah, and for K3 type, maybe I believe there are only finite many. But in general, I don't know the answer.
Okay, thank you very much.
So if you consider twisted Fourier partners, then they are infinite. Is that right?
For twisted Fourier partner,
Yeah.
right? I think there are only finite many, right? For abelian varieties and K3, only finite
Also finitely many. Oh.
Yes.
So the last theorem of degeneration of equivalence, is this very special, or is this a more general statement?
You mean this theorem or the main theorem?
Yeah, this theorem, yeah.
This is a very special one. Yeah, we cannot prove general. I asked many people. I thought this will be well known to, even for K3 and the billion surfaces. I asked the people who doing different categories like Macri or others, and they don't know such results. And for K3 and billion surface, fortunately, we have modular space. Basically, this can be transferred to us questions for modular spaces, and you can use the standard standard trick that because twisted derivative equivalence is equivalent to their x is isomorphic to the modular space of twisted stable shifts on Y.
Oh.
Okay, this isomorphism can be specialized. That's why. Because they're all not ruled, right? So isomorphism can be specialized to special fiber. So roughly speaking, this assumption can be transferred to.
Then you have always.
Yeah, transfer to this mass curly Y is isomorphic to the modular space of twisted shift on the curly X. Okay.
Yeah, but this kind can be generalized. So there is always kernel of the Fourier-Mukai factor.
Yeah, we don't use the kernel. Yeah, so that's kind of the we use the geometry. We use the isomorphism between modular space.
But this kernel produces the Mukai vector and so on.
Yeah, that I think in somehow it can be generalized in some part, but I don't know. But and a more difficult one is because here you can see that why we need P is greater than 2. The problem is if you want to use the kernel, if you want to generalize that, you need to have a twisted you need to have twisted family. Then you need a broad class can be specialized. This is hidden in this theorem. Right? Generically, on generic fiber, there are twisted derivative. That means there exists a broad class on generic fiber. But in general, people don't know whether the broad class can specialize. This is actually not correct in general. Yeah. Even for P1, the broad class is not general.
So I have another question. So you said that so isogeny doesn't imply, and so not necessarily imply the derivative equivalence, but does it imply so higher dimensional case, higher dimensional abelian varieties? And
yeah, but for higher different I think this one, this remark. It's the very beginning. Oh, here. I think this one, even you replace dbx and dby by twisted derivative equivalence, this is still still not true. Even in high dimensional, there's still counterexamples.
Yeah. So what kind of example is that?
So basically, you can just check on cohomology because I think you can construct some isogeny that doesn't imply this, doesn't have some, for this one, this just, you just check there's no symplectic isomorphisms, right? So it's easy to cook up some isogeny that doesn't have such symplectic isomorphism. And for twisted,
yes, but when twisted?
I remember I discussed with Joe a little bit about this, and let me see. Yeah, I don't have a good example in my mind, but although I think this will, yeah, because isogeny class is much larger than the isometry. Yeah, I don't know because I think there is a question that whether we have oversea, just let's work oversea,
Mm.
and whether there is a nice characterization between derived equivalence or between the twisted abelian varieties. Yeah, for abelian surface we know the answer, but for abelian varieties we don't know. So whether all of the results can be generalized to twisted abelian varieties. Yeah, I don't know whether we have such a result. If there is such a result, then maybe one can quickly cook up some examples. I remember that Whipwrecht mentioned there are some work related to this direction, but he gave some references, but I checked all the references. There's no place to mention that. So I believe this is still unknown. Yeah.
Are there more questions?